Welcome to Homework Lib.
So this question is telling us that when we calculate Fermi energy, we really should be using relativity. And in the first part, it wants us to find the number density N over V. It wants us to find what N over V is if the electric Fermi energy, the 0-point energy, is equal to 1 over 100 mc squared. So this happens when we really need to consider relativity. Okay, so how do we find that? Let's first write out the equation for 0-point Fermi energy. It's pi 4 over 3 h bar squared over 2m n over v 2 over 3. So we are extracting this n over v over here. So n over v equals, let's see, we can move 2m over here. So we'll have 2m squared c squared 2m squared c squared in the numerator, and then in the denominator we'll have 100 2 over 3 pi 4 over 3 h bar squared, and then this whole thing needs to have a power of 3 over 2. Okay. So you can see that this 3 over 2 will cancel a lot of the 2 over 3s inside this parenthesis. So we will get 2 has a power of 3 over 2. We're like putting the power into this parenthesis. Mass will become cube. C will become cube. 100 square root is 10, and then time power of 3, it becomes 1,000. So it becomes 1,000. And then 3 times 2 over 3 and 3 over 2, it goes back to 3. And then becomes pi times pi squared, and then h bar becomes h cube. If we just take this 1,000 times 3, and we can just write it as 3,000, then this is exactly the same as what this question wants us to prove. So we have proved that this is indeed the electron concentration. And then we want to calculate the numerical value. The numerical value is easy to calculate because everything is just, it's either non or constant. Mass is 9.1 times 10 to the negative 31 kilogram cube times 3 times 10 to the 8 meter per second cube. 3,000 times pi squared, pi times 10 to the negative 34 joule second cube. And this gives us 1.67 times 10 to the 33 per cube. So this is going to be the number density. Oh, all right, so let's move on to part B. Part B says if we ignore relativistic effect in a metal such as copper, then the electron concentration will be small n is 8.45 times 10 to the 28 per meter cube. And then if this is electron concentration, will it be a good idea to ignore the amount of relativistic effect in copper? And the answer is that, well, we can compare it to part A. If look at part A, we have 10 to the 33, and now we only have 10 to the 28th. So it's like 10 to the 5th times smaller. It's like smaller than part A by 10 to the 5th times. So you can see that the concentration of electron in copper is very, very, very small. So because this is so small, it is very safe to ignore relativistic effect, because the electron density should be like 10,000 or like 100,000 times larger for relativistic effect to really be important. So we can ignore it. And then if we look at part C asks us to look at white dwarf. A white dwarf star it gives us a lot of information, but then we want to estimate the electron concentration with a white dwarf. So if we, part A, we can consider the white dwarf as if it is made of carbon, which has a mass per atom of 1.99 times 10 to the negative 26 kilogram. Okay, so let's first find the number of electrons. The number of electrons can be given by the total mass, which is 2 times 10 to the 30 kilograms, that is the mass of the white dwarf, over the number per atom is 1.99 times 10 to the negative 26 kilogram. And at the same time, it's a carbon atom, so we have 6 electrons in each atom. So we have to multiply this whole thing by 6. So we will have 6.03 times 10 to the 56. So this is going to be the number of atoms we have. And then we also need to find its density. So the concentration can be found, so small n equals big N over the volume. And the volume can be found by assuming this is a ball, this is a sphere, and then we can have 4 over 3 pi r cubed. And r, the radius of the white dwarf, was said to be 10 to the 6 meter cube. And this is 6.66 times 10 to the 35. Meter percent. Okay, and then we can compare this to what we found in part A, and we can see that a white dwarf it's very relativistic because this density is around 300 or 400 times the density that where relativistic effect would become relevant. So in this case, because the density for electron is so large, relativistic effect will be very important when we are looking at the white dwarf.